Hello, welcome. My name is Cory, and today I'm going to be walking you through the Stope Shape Optimizer tool in GEOVIA Surpac. It is a tool that runs on the Alfred Mining Solutions engine in the background and is found under the Design Stope Shape Optimizer menu, along with the multiple and in bulk options, both of which will just run the Stope Shape Optimizer iteratively so that you don't have to run it multiple times manually each time. The function is designed to take a block model, break it into tubes, which is subdivisions of the model, and place slices through the depth of the model to determine the optimal width of a stope. It will then output an SDM file that contains your grade data, your volumes, your tons, etc., for the purpose of design work, engineering, and scheduling down the road. We are going to run through a demo as if we have been given this block model with these geology surfaces as guide points. So we will go to Design, Stope Shape Optimizer, Stope Shape Optimizer. There's quite a few boxes and functions in here to fill out, boxes to fill out. So fortunately, we have our Surpac contextual help menu for more information at the bottom left. It will open up to the Stope Shape Optimizer page. And if we hover over any of these radio buttons, we're going to get our contextual field help as well for help in filling this out for more information. So I'll begin by giving it a project folder. I'll use my working directory by default and a project name. I'll use webinar test. If we had an existing project and we wanted to continue working, we can specify it here at the top, and it will just load in with all of the attributes that we fill in. It will, because we have a block model open, it will populate it here. Otherwise, we would use the three dots to find our block model, and we give it a description. We'll check on to use multi-threading. It's off by default as it is a relatively new feature, as is Surpac standard. But turning it on, we have found much, much faster as a result, like exponentially faster. So very much worth turning it on. The stope shape method, the slice method, will, as I mentioned, go the entire depth of the model through to determine the optimal depth of stopes. The boundary surface method, if we have a thin lens or something with more narrow refinement required, we can use that. A very thin gold seam, for instance, might use the boundary surface method. Stope optimization method, either it's vertical slices in the X, Z, or Y, Z directions, and then done through the depth of the stope to determine the optimal size, or a horizontal slice in the plan view, and then gone upwards to determine the optimal height. In output customization, the mandatory fields to fill out here are the stope solid file, the detailed report file name, and a description field. I like to use the same name for everything here because then when the output is created, it will group it all together in the working folder, so it's a little easier to find everything. You can also create optional fields here, optional outputs, the stope string file, tube solid file, verification solid, summary file, subeconomic stope file, etc. And we can define the colors for our stopes, our subeconomic stopes, our pillar, our failed seed, our etc. Any of these, or we can leave them defaults. The subeconomic stope, which we can choose to output, is a stope that is above zero but below our cutoff, and a failed result is a stope that is created above our cutoff but then filtered out at the end of the process here. So we can choose to output those if we like. I am not going to for this run. Under categories reported, there's total, summary, and all. So this is just how much does it discretize the waste data into different categories, essentially. Total being a single number, summary is a little bit of discretization, and then all would be every individual category. So I'm just going to go with total. And we can rename our stope reporting mass field if we like, and I'm not going to. We can do additional reporting fields here. So by default, it will report out our optimization field, which will be NSR for the purpose of this demo, net smelter revenue. This is just the attribute that I am comfortable with myself, but you can also optimize on grades or block value or any field that you want to choose to optimize on. Because you have to optimize on a single value, you would then specify here if you want to report out any additional fields. So if we're optimizing on NSR, but we want to report out our gold, silver, and copper, we can choose to do so. We can also exclude fields from our report. So if we want, say, to exclude blocks with a certain rock type or a certain category, if we want to report out only mining and indicated but not inferred, for instance, we can exclude inferred from our report that gets generated. You can also specify object IDs. By default, it'll be 1, 2, and 3. You can use whichever convention you use in your mine site. For our Stope framework now, this is where we specify the framework of the optimization. So I mentioned it's going to section our block model into tubes. What it will actually do is segment our framework into tubes. So we can specify our framework here. Now, usually your framework is going to be the same as your block model. It does not have to be. You can have a rotated framework so that your stopes are in a rotated direction to your block model. But usually, at least for a first run, we're going to follow the block orientation. I clicked on Recalculate Framework Extents. If you do not see anything in the box there, just do so. And if these change for whatever reason, you can click on the Refresh button and it will just refresh them with whatever your open extents are. You can click to display the bounding box if you would like. If you have a block model that is constrained, for instance, you can find the bounding box for the framework and work with that. Because it is the framework, if we have a rotated framework, it may not align with the block model, so you just might need to expand it to encompass the entire block model. And the bounding box can help visualize that. For a segmentation option, we can do fixed sections and levels, variable sections and levels, or some combination thereof, or we can use different shapes, string levels, defined polytubes, all these different options for essentially the same thing, really, which is just how are we breaking up the framework. We're going to use fixed sections and levels for this particular optimization. And what we are going to do here is we're going to do distances of 20 wide by 40 tall, just to get 8 by 4 grid for our tubes. The stope orientation plane can either be XZ or YZ. In our case, it will be XZ, so it will break them up in this direction here, and it will go down the depth this way. We can also break them up here, and it will go down the depth this way if we choose to. You can choose to enable ore development control if you have ore development that you want to keep track of, development sizes for your drifts. We don't have any in this case. Our slice definition is now how are we going to define our slices? And I am actually going to skip this tab for a second and come back to it. I'm going to define the stope geometry first. In the stope geometry, we specify our allowed size for our stopes. Now, if I want to create as many stopes as possible, I'm going to give it a very small stope width. Width in this case being depth down the stope. And I'm going to give it my maximum in this case is going to be 40. It's going to be the same as my height of the stope. A minimum pillar width, so this is going to be the minimum gap between two stopes that are created. In this case, I'll put 4. This is just a number that I like to start with, but if you have different requirements, different geology requirements on your site, you can specify your actual minimum pillar width. And a minimum side ratio. So this is going to be, when it creates the sides, how long can one be as opposed to the other? So if one can be 40 wide and one can be 20, that would be a side ratio of 2. I'm going to create a side ratio of 1.5 here, just to give it a bit of flexibility, but these can be much smaller. And you can have dilution skin. So local versus use block model. If you have a dilution skin, you can either create a set distance, or you can use the block model to specify different distances for your footwall and hanging walls. What this will do is for the purpose of the optimization, it will add some dilution around the stope, but then your report out at the end will be just the stope itself and not the dilution. Next is the angles. So when we create the front and back of the stope, don't necessarily have to be at 90-degree angles to create a cube. They can be more of a trapezoidal shape or very complex with different dips and angles of the front and back of the stopes. Here's where we would specify that. You can either have the same constraints for the front and back, or you can have different near and far constraints. I like to be as general as possible here for a first run and then narrow it down as I go. But if you have any specific geology requirements, obviously start with those. For these, if I don't know any properties of the block model or the mine itself, I'm going to begin with 60 to 120 with a max change of 90. And that just means that it can be 60 degrees dip in the front to a 120 when it creates that slice. So that slice can be created, the front of the stope and the back of the stope can be at a 60 to 120 with a maximum change between them of 90, which is very broad. For the strike angles, I will do -45 to 45 with a maximum change of 20. So the strike being, if we're looking in plan view, the distance like that, the angles there of the front and back of the stope, with a maximum waste fraction of 1. Now, the reason I skipped slice definition, I'm going to go back now, is because in slice definition, we have our default strike and default dip. Those two values need to be within these ranges here. And if you have different near and far constraints, then they need to be within either of them. So if you have, here I'm doing 60 to 120. If you had 60 to 120 or 80 to 140, it would the default would need to be between 80 and 120, whatever the smallest range is there. So in this case, I will use a default strike of 0. It is between those two, and a default dip of 90. For a slice interval, it will default to 2. We can change that if we like by clicking on the checkbox and then changing it. I'm just going to use the automated generator value of 2. For the stope control, you can use surface or use model. I have a surface that I will use, so I will do so. If you do not have a surface which provides a starting seed for the slices, for the strike and the dip, then it will just use the entire model and it will use your default strike and dip each time, or you can use the model if you have dip direction and dip values with some defaults. I'm going to use the surface. Going back to stope geometry, these two tabs now, stope shape refinement and stope and constraint to structure, are just ways of refining and constraining the stopes that get generated. So under stope shape refinement, it is by default, the only thing that will be checked on is full shapes. It will output the full stopes. We can output subshapes if, for instance, there are if you can create half-size shapes in a direction that is optimal, but then the full shape isn't, it can do so. Development, if we have a development for our drifts, we can add it here and it will factor it in. We can also enable refinement. By default, our slices will have 4 points, 1 at each corner. We can change that to be 6 points or 8 points around. And what this will do is allow it to have convex options. 6 will add an additional point in the vertical direction so that I can concave in on the sides, and 8 will allow it to be concave or convex the whole way around. We can add our tolerances for concavity and convexity, and then our middle point ranges for where it can actually put those middle points in the stope. For post-processing, we can have smoothing, which means that when we are looking at the faces and we look at the corner of one and the next corner of the next, how jagged can they be? How offset can they be? Smoothing allows for them to try and be as smooth as possible, those corners. We can split or merge stopes together. These are inverses of the same idea, which is just that if they are too big, and within certain tolerances, it will split them into sub-stopes and put a pillar between them. Or if they are too small, they can be merged again within tolerances. And then we can see our merged stopes. And you'll see that it actually outputs a separate merged stope file. So we'll output the original stopes and the merged stopes. We can also enforce alignment, and this is useful if you have very narrow veins. So if you were looking at the input here for the boundary surface method, this is going to be useful for forcing the stopes to align to the vein. Essentially, you can align the center, the front, the back, the near far, or the hanging wall, and then the cutoffs for those sort of alignments. For constraint to structure, we can constrain to a geological structure for overbreak, which means that if you have, say, a topography, and if you get within a certain distance of the topography, it will collapse it, so that if it reaches that height, just include the entirety of it. That's what this is for, and we have the option to expand or snap to for overbreak. The stope material constraints, we can enforce stopes to contain a specific material. So we are saying if we have say measured, indicated, and inferred, we can force any stopes created to have measured a certain amount of measured in it, as an example. This also applies to any other rock types. I'm just using measured, indicated, and inferred for this explanation. Similarly, for exclusion, we can exclude attributes. So if we want to say that stopes cannot have any inferred or have a maximum amount of a given inferred, then we can specify that here. We can also exclude material by distance, but all of these really do the same thing. And then for stope zone mixing field, we can have stopes be exclusive by a zone code so that a stope of material A cannot contain any of material B, for instance. So this would be our field values for not mixing those blocks together for the reporting. Next is the cutoff. Now I mentioned that we are going to be using NSR for this. Here's where you would specify that. So optimize cutoff using either grade, value, or calculated value. Grade is anything where it will then multiply it by a tonnage. Value is going to be anything where it is an aggregated value, so not multiplied by tonnage. And then calculated value is going to be if it is a grade, but then you are also doing a calculation with prices, costs, royalties, etc. and recoveries. So we're going to be using value, which is what NSR is, and we will specify that here. You can specify a default for any missing values. Under density, you'll specify your density and give a default for any missing values. You can choose to allow for zero density if you have any voids or mined out areas underground, and you can choose to maximize total metal if you would like. So the optimization by default will try to get the highest value of from the cutoff, but you can also choose to maximize the amount of metal you get, even if it would technically result in a lower value. So this would be useful if you are using the calculated value attribute. It might give a different value, a different result. Our single value cutoff, you can choose either a single value, you can choose to be from model if you have different cutoffs by zone, and you can vary it based on elevation, height, area, etc. We're going to be using a single value cutoff of 50 for this one. And finally, you can choose to use the head grade evaluation. And what this does is sometimes the value in situ is different from the value that would be the cutoff at the processing plant. And this allows you to have that account for that discrepancy by checking that on. You can choose a single value head grade or a different head grade by area above the cutoff. Under optimization control, for evaluation method, there are three choices: fast, precise, or fast evaluation with precise report. Fast and precise are a bit of a misnomer and really just refer to the two different algorithms that are being used. The precise algorithm is doing exactly as I described, where it is doing adding the slice, doing the calculation, determining if it's better. Adding a slice, manipulating it, doing the calculation, determining if it's better. Fast is going to be using some more advanced ray tracing style techniques on in the algorithm to try and speed that up a bit and make logical jumps. Whereas precise is doing every step. So you can do either fast, where it will do both. It will do those ray tracing style, those advanced sort of jumps to try and get a faster result out, and then report those shapes that it determines using the same sort of fast method. The fast is using the strike and vertical intervals so that it is kind of breaking it up into doing these sort of just quicker algorithm. Some of these algorithms are very proprietary, so it's very difficult to talk about what they're exactly doing. The precise is going to be doing it step by step, and then you can choose the fast evaluation precise report, where it will do the faster stope generation, but then a very precise report from it. Precise will be longer than fast to do in this case. Generally speaking, for a first run through, do fast. For a mid run through where you're refining things, you might want fast evaluation, precise report. And then maybe if you want to just be 100% sure of all your things at the end, do a precise final run. Strike interval and vertical interval are going to be how you break up the model for determining how you break up the stope shape for this process, this faster process. Dip and width parameter conventions is if it is using the framework dip and width, or if it's using the true world dip and width for its evaluations. Apparent is the most common in this case. If you would like to use testing shapes for to determine how the algorithm is working and see how the annealing is working, annealing being that process of put a slice, alter it, determine if it's better. Then you can check that on to determine. This is a little bit more advanced for really tracking and verifying what it is doing. And really, if the results you're getting don't look like they're off, I will not be using it here. Filtering expressions, the annealing, you can either filter on the annealing process, which is the input, or you can filter on the results, which is the output. And really, so if you filter on the annealing process, it stops stopes from being created. If you filter on the results, the stopes get created, and then it does not get reported in the output. The pillar requirements here, you can choose to ignore the pillar requirements between the parallel full and subshapes and between split shapes if you would like. It will always have the pillar distance in the stope geometry inputs is required still, but you can check on to ignore it. You can have a different dip corner width test, in which case it will test the different corners to see if they have similar dips. So if you need your dips to kind of align for geology reasons, then this would be a checkbox to check on to see what the different result is. The check result with dilution included, as mentioned, it will not actually use dilution in the results. This allows you to output that dilution in the results, not just in the optimization process. You can also use a different minimum offset distance when annealing. So by default, the minimum distance will be 0. It will step them step by step. You can sort of add jumps to that in the annealing process for the purpose of that minimum distance. These are all just ways of sort of affecting that result based on your specific geology. This is a very geology-dependent tool. Once all that's filled in, we're going to hit Run. And because we are using the multi-threading option, this will run very quickly. You'll see at the bottom. This is a process that would take previously a good 10 or 20 minutes to run. Now it's going to be done in 20 seconds. So much faster. As mentioned, this is a very geology-dependent one. So not every block model is going to be a very bulky football-shaped block model or zone. The seams might not be this nicely structured. You might need a lot more shapes, for instance. So all of those values can be adjusted based on your specific needs. Yeah, we're already at 97%. Now, the output from these stopes are going to contain your grade data, your volume, your tonnage data. They may need some additional refinement. We'll cover in a future webinar how to refine those shapes and how to prepare them from getting ready into a scheduling program. So when it's saying that the quad that it's testing there, it's breaking it into quadrants for the purpose of the testing and for the annealing process that it is doing. So that was that testing shapes dialog box at the end. There we go. And then what we can do is open up our webinar test.sdm. And this will be our stope. So I'll close my block model now. And we can see that it created these stopes and it followed that grid shape, that seam that we have provided by our geology team as a starting point. Now these stopes are going to be SDM files. This created a very thin stope, you can see, for instance, here, and then a very thick stope behind it. So this material in between, splitting it up, created more value. It created an SDM file. We can see on the left here that it output our tons, our volume, our NSR, and our density for that stope because we did not report out any additional fields. Looking at the block model, not block model, design stope shape optimizer multiple function now. This just allows you to load in multiple project names, multiple project files at once, and then run them sequentially. The design stope shape optimizer in bulk function allows you to specify multiple projects, but then also put a varying cutoff head grade or minimum pillar width to allow it to vary those as well between them. So you can end up with different, if you want to analyze the effect of increased or decreased cutoff on a similar project file. That has been the Stope Shape Optimizer tool. If you'd like further information, please let us know.